Detrital zircon geochronology is the science of analyzing the age of zircons deposited within a specific sedimentary unit by examining their inherent radioisotopes, most commonly the uranium-lead ratio. The chemical name of zircon is zirconium silicate and its corresponding chemical formula is Zr silicon oxide. Zircon is a common accessory, a trace mineral constituent of most granite and felsic igneous rocks. Due to its hardness, durability and chemical inertness, zircon persists in sedimentary deposits and is a common constituent of most sands. Zircons contain trace amounts of uranium and thorium and can be dated using several modern analytical techniques. It has become increasingly popular in geological studies from the 2000s, mainly due to the advancement in radiometric dating techniques. Detrital zircon age data can be used to constrain the maximum depositional age, determine provenance, and reconstruct the tectonic setting on a regional scale. Detrital zircon origin. Detrital zircons are part of the sediment derived from weathering and erosion of pre-existing rocks. Since zircons are heavy and highly resistant at Earth's surface, many zircons are transported, deposited and preserved as detrital zircon grains in sedimentary rocks. See Figure 2. Note that the diagram is used for concept illustration. Detrital zircon in reality can be products from all kinds of rocks, not necessarily igneous rocks. Properties. Detrital zircons usually retain similar properties as their parent igneous rocks, such as age, rough size and mineral chemistry. However, the composition of detrital zircons is not entirely controlled by the crystallization of the zircon mineral. In fact, many of them are modified by later processes in the sedimentary cycle. Depending on the degree of physical sorting, mechanical abrasion and dissolution, a detrital zircon grain may lose some of its inherent features and gain some overprinted properties like rounded shape and smaller size. On a larger scale, two or more tribes of detrital zircons from different origins may deposit within the same sedimentary basin. This gives rise to a natural complexity of associating detrital zircon populations and their sources. Zircon is a strong tool for uranium lead age determination because of its inherent properties. Zircon contains high amount of uranium for machine recognition, commonly 100,000 ppm. Zircon has a low amount of lead during crystallization, in parts per trillion. Thus, lead found in zircon can be assumed as daughter nuclei from parent uranium. Zircon crystals grow between 600 and 1100 degrees Celsius, while lead is retained within the crystal structure below 800 degrees Celsius. See closure temperature. So once zircon has cooled below 800 degrees Celsius, it retains all the lead from the radioactive decay. Therefore, UPB age can be treated as the age of crystallization. If the mineral sample itself has not undergo high-temperature metamorphism after formation, zircon commonly crystallizes in felsic igneous rocks, with greater than 60% silicon oxide content. These rocks are generally less dense and more buoyant. They sit high in the Earth's continental crust, and have good preservation potential. Zircon is physically and chemically resistant, so it is more likely to be preserved in the sedimentary cycle. Zircon contains other elements which give supplementary information, such as hafnium, HF, uranium, thorium, U/Th ratio. Sample collection. There are no set rules for sample selection in detrital zircon geochronology studies. The objective and scale of the research project govern the type and number of samples taken. In some cases, the sedimentary rock type and depositional setting can significantly affect the final result. Examples include matured quartz arenite with inflorescence formation yield older and more diverse ages given by well-rounded detrital zircons, which may correlate to multiple sedimentary reworking events. On the contrary, harmony formation in the same region has younger and homogeneous ages given by euhedral detrital zircons. These two formations illustrate the possibility of relating sedimentary maturity with resulting zircon ages, meaning that rounded and well-sorted sedimentary rocks, e.g., siltstone and mudstone, may have older and more diverse ages. Turbidites in Hart's Pass formation contain homogeneous detrital zircons ages. On the other hand, fluvial Winthrop formation in another strata of the same basin has various detrital zircon age populations. Comparing the vertical detrital zircon distribution within these two formations, one can expect a narrower age population of detrital zircons from rocks which are rapidly deposited, such as turbidites. Rocks that are gradually deposited, e.g., marine mudstone, however, have a greater chance and time to incorporate zircon sediments from different localities. Detrital zircon extraction. After rock samples are collected, they are cleaned, chipped, crushed and milled through standardized procedures. Then, detrital zircons are separated from the fine rock powder by three different ways, namely gravity separation using water, magnetic separation, and gravity separation using heavy liquid. In the process, grains are also sieved according to their size. The commonly used grain size for detrital zircon provenance analysis is 63 to 125 micrometers, which is equivalent to fine sand grain size. Type of detrital zircon analysis. There are two main types of detrital zircon analysis: qualitative analysis and quantitative analysis. The biggest advantage of qualitative analysis is being able to uncover all possible origin of the sedimentary unit, whereas quantitative analysis should allow meaningful comparison of proportions in the sample. Qualitative analysis. Qualitative approach examines all the available detrital zircons individually regardless of their abundance among all grains. This approach is usually conducted with high-precision thermal ionization mass spectrometry, TIMS, and sometimes secondary ion mass spectrometry, SIMS. Optical examination and classification of detrital zircon grains are commonly included in qualitative studies through backscatter electrons, BSE, or cathodoluminescence, CL, imagery. Despite the relationship between the age and optical classification of detrital zircon grains is not always reliable. Quantitative analysis. Quantitative approach requires large number of grain analyses within a sample rock in order to represent the overall detrital zircon population statistically, i.e., the total number of analyses should achieve an appropriate level of confidence. Because of the large sample size, secondary ion mass spectrometry, SIMS, and laser ablation inductively coupled plasma mass spectrometry, LAICPMS, are used instead of thermal ionization mass spectrometry, TIMS. In this case, BSE and CL imagery are applied to select the best spot on a zircon grain for acquiring reliable age. Methodology. Different methods in detrital zircon analysis yield different results. Generally, researchers would include the methods, analytical instruments they used within their studies. There are generally three categories, which are the instrument S used for zircon analysis, their calibration standards, and instrument S used for zircon imagery. Details are listed in Table 1. Detrital zircon data. Depending on the detrital zircon study, there should be different variables included for analysis. There are two main types of data: analyzed zircon data, quantifiable data and imagery, descriptive data, and sample, where they extract the zircon grains. Data details are listed in Table 2. Filtering detrital zircon data. All data acquired first-hand should be cleansed before using to avoid error. Normally by computer, by UPBH discordance. Before applying detrital zircon ages, they should be evaluated and screened accordingly. In most cases, data are compared with UPB Concordia graphically for a large dataset. However, data with high UPBH discordance, greater than 10 to 30%, are filtered out numerically. The acceptable discordance level is often adjusted with the age of the detrital zircon, since older population should experience higher chances of alteration and project higher discordance. See uranium lead dating, by choosing the best age. Because of the intrinsic uncertainties within the three yield UPB ages. 207 petabits, 235 U. 206 petabits, 238 U and 207 petabits, 206 petabits. The age at approximately 1.4 GHz has the poorest resolution. An overall consensus for age with higher accuracy is to adopt 207 petabits, 206 petabits for ages older than 0.8 to 1.0 GHz. 206 petabits, 238 U for ages younger than 0.8 to 1.0 GHz. By data clustering, given the possibility of concordant yet incorrect detrital zircon UPB ages associated with lead loss or inclusion of older components, some scientists apply data selection through clustering and comparing the ages. 3 or more data overlapping within plus or minus 2 sigma uncertainty would be classified as a valid age population of a particular source origin. By age uncertainty, plus or minus sigma, there are no set limit for age uncertainty and the cutoff value varies with different precision requirement. Although excluding data with huge age uncertainty would enhance the overall zircon grain age accuracy, over-elimination may lower overall research reliability, decrease in size of the database. The best practice would be to filter accordingly, i.e., setting the cutoff error to eliminate reasonable portion of the dataset, say less than 5% of the total ages available, by applied analytical methods, depending on the required analytical accuracy. Researchers may filter data via their analytical instruments. Generally, researchers use only the data from sensitive high-resolution ion microprobe (SHRIMP), inductively coupled plasma mass spectrometry (LAICPMS), and thermal ionization mass spectrometry (TIMS), because of their high precision, 1 to 2%. 1 to 2% and 0.1% respectively. In spot analysis, an older analytical technique, lead evaporation, is no longer used since it cannot determine the UPB concordance of the age data by spot nature. Apart from analytical methods, researchers would isolate core or rim ages for analysis. Normally, core ages would be used as crystallization ages. They are first generated and least disturbed part in zircon grains. On the other hand, rim ages can be used to track peak metamorphism as they are first in contact with certain temperature and pressure condition. Researchers may utilize these different spot natures to reconstruct the geological history of a basin. Application of detrital zircon ages. Maximum depositional age. One of the most important information we can get from detrital zircon ages is the maximum depositional age of the referring sedimentary unit. The sedimentary unit cannot be older than the youngest age of the analyzed detrital zircons, because the zircon should have existed before the rock formation. This provides useful age information to rock strata where fossils are unavailable, such as the terrestrial successions during Precambrian or Pre-Devonian times. Practically, maximum depositional age is averaged from a cluster of youngest age data at the peak in age probability, because the youngest UPB age within a sample is almost always younger with uncertainty. Tectonic studies equals using detrital zircon age abundance equals. In a global scale, detrital zircon age abundance can be used as a tool to infer significant tectonic events in the past. In Earth's history, the abundance of magmatic age peaks during periods of supercontinent assembly. This is because supercontinent provides a major crustal envelope selectively preserve the felsic magmatic rocks, resulting from partial melts. Thus, many detrital zircons originate from these igneous provenance, resulting similar age peak records. For instance, the peak at about 0.6 to 0.7 Ga and 2.7 Ga, Figure 6, may correlate the breakup of Rodinia and supercontinent Kenwarland respectively. Equals using difference between detrital zircons crystallization ages and their corresponding maximum depositional age equals. Apart from the detrital zircon age abundance difference between detrital zircons crystallization ages, Ca, and their corresponding maximum depositional age, Dr, can be plotted in cumulative distribution function to correlate particular tectonic regime in the past. The effect of different tectonic settings on the difference between Ca and Dr is illustrated in Figure 7 and summarized in Table 3.